My name is Abigaba Patient Sarah, and our project title is Graph-Based Reasoning for Preeclampsia Self-Screening using Accessible Biomarkers. So let us dive into what me and my group members were able to do in relation to our project. So preeclampsia is a pregnancy disorder, and if not detected at an early stage, it results into high maternal deaths. We realized that in low-resource settings in Uganda, this condition is not detected at an early stage, which results into severe conditions. We realized that early screening is not possible due to various reasons. For example, laboratory limitations as well as lack of medical expertise. So preeclampsia screening, this is the early detection and assessment of the risk level of preeclampsia among the pregnant women. Accessible biomarkers, these are measurable indicators, for example, urine proteins, which we can use in order to identify the presence or the risk level of any condition or disease. Maternal health diagnostics, this refers to the assessment and detection of health conditions that affect the pregnant women in order to improve maternal health and well-being of the society. So we looked at the different works that people had done earlier, especially the graph-related work, since we're dealing with graph-based models, in order to get an insight of what they did, which conditions did they, which limitations did they face, how did they overcome them, and through that we're able to get an insight of what we were to do in regards to our project. So as we had looked at preeclampsia, the definition, we realized that it affects 10% of the Ugandans, and it affects 50, and in affecting 10% of the pregnancies in Uganda, it results into 15% maternal deaths if not detected at an early stage. So through that, we had to get aware of how this was going to be solved. So we had our inputs, which consisted of demographic data, for example, the age, the gravidity, the parity, the laboratory data, for example, the protein level, the platelet count, as well as the vital signs, for example, systolic and diastolic blood pressure. So from these inputs, our graph-based models were to learn in their unique ways in order to do binary classification of either high or low risk of preeclampsia. So one of our research objectives were to develop a supervised machine learning framework that is able to do the binary classification of preeclampsia. Another objective was to implement as well as compare these graph neural network models, for example, GAT and RGCN. And from these objectives, we posed and asked ourselves some questions. How are we going to develop this supervised machine learning framework, and how are we going to compare the performance of the models such as GAT and RGCN? So through that, we had some contributions. For example, we were able to compare the models GAT and RGCN using different evaluation matrices, for example, F1 score, precision, and we were able to develop a lightweight deployable edge AI to be used in the prediction of preeclampsia. So let us look at the methodology and system architecture of our system. So when we acquired our data was basically in a tabular form with different features. We had to do some data cleaning to remove to fill the missing values, to handle some features that are not relevant in the medical sector, in order for, and this data cleaning enables our models to work with our data set. After the data cleaning was done, we had to do the graph formation, since we're dealing with basically graph-based models. And from that, our models learned from the graph in their different ways. After the different individual models, the GAT and RGCN learning, we had our ensembled model, which combined GAT and RGCN, and it did the binary classification of either high or low risk of preeclampsia. So let us look at the architecture of RGCN. So when we get our inputs, for example, the age and the proteins, and we input them there, these work as the features for the different nodes that we constructed, and the nodes have the features that we input there, and the edges the edges show the relationships between those nodes. So basically, RGCN works with learning the relations between the features that we input there, and the layer 1 learns the hidden patterns between those relationships, and layer 2 bases on those on how layer 1 has been able to learn from those patterns in order to produce a probability. And with the use of the log softmax function, it is able to output a probability that we can understand of either a high risk of preeclampsia or low risk of preeclampsia. So basically, this explains what what was in the diagram, and from this first step, it shows how the tabular data is converted into a graph-based structure in which our model can be able to learn from. And then this shows the layer-wise propagation, how layer 1 learns, and how layer 2 learns, and how the softmax function does the output. So GAT is also a graph-based model, but its only difference is that it adds more weight to features that are relevant to preeclampsia prediction. For example, if you have features such as systolic blood pressure, diastolic blood pressure, then if we have another demographic data such as level of education, which is not relevant to prediction of preeclampsia, it will attach more weights to systolic and diastolic blood pressure and not attach more weights to the level of education. And from that, it will be able to do the binary classification of either high or low risk of preeclampsia. So after training the individual GAT and RGCN models, we assembled them, and the ensemble combines the individual models, which are GAT and RGCN, in order to be able to do its binary classification of either high or low risk of preeclampsia. So this is basically the model architecture. And if we look at the ensemble principle, our ensembled model is able to produce one represents high risk if from the pairs we used a weighted average ensemble, and if from that pair the total is greater than 0.5, it will produce a high risk, and if it is less than 0.5, it will produce a low risk of preeclampsia. So after looking at our different models, let us look at our data set. Our data set was, as I described it earlier, it was in tabular form with different features such as age, gravidity, systolic and diastolic blood pressure. And our main objective was to be able to identify the clinical features that are relevant to preeclampsia prediction. So we had to do some EDA on our model, and our shape was, as you can see, it was 243. However, we realized that our dataset had some issues. For example, some age ranges were not relevant. Then parity cannot be greater than gravidity. It is medically impossible. So after doing this EDA, we had to do some data preprocessing in order to work on the different issues that were on the dataset. For example, the issue of gravidity and parity, we had to drop that cases because it is medically impossible for parity to be greater than gravidity. We also had to fill in the missing values in the different columns in an appropriate way. After the data preprocessing was done and some feature engineering was done, our final dataset shape was 241 patients and 33 features. So this graph mainly shows the most relevant features in relation to preeclampsia prediction. So since we are dealing with graph-based models, we had to create a graph. And as you see, we have the nodes, which were 12 for 1, and the features, which were 40. So after the graph was constructed, and we did the model training, the testing and validation, this was how each of the different models performed, and the evaluation matrices we used were AUC, F1 score, precision, recall, as well as accuracy. So from these evaluation matrices, we had to select a model to deploy. And since we are dealing with the medical sector, the best evaluation metric that we would base on to select a model to deploy is recall. Since recall basically deals with being able to identify most true positives, it is very dangerous for our system to flag a positive case as a normal case, because if it goes unnoticed, the person will be like, oh, I'm normal, and yet they have preeclampsia, which is very hazardous. And our main aim is to be able to detect preeclampsia at an early stage. So if you look at the evaluation matrices and you look at recall, we realize that the ensemble of RGCN and GAT performed better than the individual models, and thus we selected it for our deployment. We saved our model as our ensemble model as a JSON file, and the JSON file was serialized, which means it was converted in a format that can easily be stored and transmitted. From there, the Flask API reads and loads the model logic. So from there, we did the deployment where the Flask API is deployed on Render Cloud. And from there, we used Flutter in order to develop our front end, which is the user interface, how the people are going to be inputting in their information. We used Flutter. So this basically shows the model selection and deployment pipeline as I described earlier on. So this screenshot shows how our user interface looks like, and from this link, if you tap on it, you can be able to access our user interface and be able to do your self-screening. As we were working, we were faced with some limitations. For example, our data set was really small. Its shape was really small, as you had seen, and this resulted into overfitting. Then initially, our final product had to consist of the user being able to input to take a picture of the endema, the swollen feet and hands, and also their dipstick. However, we failed to get a large data set to be able to train and deploy, so it was also a limitation. Despite all these limitations, we were able to ensemble GAT and RGCN, and it really worked well in our predictions. However, we intend to get a bigger data set. Since we worked with a really small data set, we intend to get a bigger data set to be able to work on, and also work on it using more advanced graph-based models. We also intend to either create or get an endema and urine data set in order to use it. Thank you.